Hello, my dear students. Welcome to ESR Chemistry classes. Here we are in lecture number 3 on ESR spectroscopy, which is an important topic of inorganic spectroscopy. Let us first of all see the solution of homework given in the previous video. There were two problems for homework. The first one is here. At what magnetic field strength would methyl free radical come into resonance in a spectrometer operating at 9.5 gigahertz if the G value is 2.0026? Its solution is given here. We already know that this is the resonance condition. The energy of EMR absorbed should be equal to the energy difference between two spin states of the electron. We have to calculate B, that is the strength of applied magnetic field, and therefore B will be equal to h nu divided by G beta, and the value of h is 6.626 into 10 to the power minus 27 arg second, and the frequency of EMR at which the spectrometer operates is 9.5 gigahertz, and giga means 10 to the power 9. It is 9.5 into 10 to the power 9 hertz, that is per second. The value of G is given here 2.0026, and the value of beta we have already calculated in the previous video. It is equal to 9.27 into 10 to the power minus 21 arg per Gauss, and the overall unit of B is Gauss. On solving this expression, we get B is equal to 3391 Gauss. It means methyl free radical will come into resonance at an applied magnetic field strength of 3391 Gauss in a spectrometer which operates at 9.5 gigahertz. There was another problem for homework in the previous video, and it is calculate the frequency of EMR absorbed during resonance of an electron from ms equals to minus half to ms equals to plus half in a magnetic field strength of 0.35 Tesla. We have to calculate the frequency of EMR which will be absorbed during the transition of electron from ms equals to minus half to ms equals to plus half in a applied magnetic field strength of 0.35 Tesla. Its solution is given here. H nu should be equal to G beta B for the resonance of a spin of electron from ms equals to minus half to ms equals to plus half, and we have to calculate nu here. Nu will be equal to G beta B divided by H, and on putting the values of different terms, we have this one. Nu will be equal to 2.0023 into 9.27 into 10 to the power minus 21 multiplied by, we already know that 1 Tesla is equal to 10 to the power 4 Gauss, and therefore 0.35 Tesla will be equal to 3500 Gauss, and the value of h is given here. The overall unit will be per second, and on solving this expression, nu will be equal to 9.8 into 10 to the power 9 per second. Per second is known as hertz, and 10 to the power 9 is known as giga, and the answer may be written as nu is equal to 9.8 gigahertz. It means the free electron will exhibit resonance from ms equals to minus half to ms equals to plus half in a spectrometer of operating at applied magnetic strength of 0.35 Tesla by absorbing this electromagnetic radiation. Relative population of spin states of electron. The spin quantum number of electron is 1 by 2, and its magnetic spin quantum numbers are plus minus half. But in the absence of external magnetic field, these two spin states of electron have the same energy, that is, are degenerate. If an external magnetic field of strength B is applied, these two spin states of electron remain no more degenerate. They are split up into two spin states. The spin state of electron with ms equals to minus half, that is beta spin, has lower energy, while the spin state of electron with ms equals to plus half, that is alpha spin, has higher energy. This is higher energy level and this is lower energy level. The population of lower energy level is n minus half, while the population of higher energy level is n plus half. The population, that is n plus half, of higher energy level, higher energy spin state of electron, that is ms equals to plus half or alpha spin. The population of higher energy spin state of electron, that is ms equals to plus half or alpha spin, relative to the population of lower energy spin state, that is ms equals to minus half or beta spin, can be given by Boltzmann distribution law. The population of this higher energy spin state of electron relative to the lower energy spin state of electron can be given by Boltzmann distribution law, and this law is given here. The population of higher energy state divided by the population of lower energy state will be equal to e to the power minus delta E by kT, where K is Boltzmann constant, T is temperature, and delta E is the energy difference between two energy levels. And this energy difference in the present case is G B beta, and therefore G B beta can be written in place of delta E. Thus, the population of higher energy spin state of electron relative to the lower energy spin state of electron is equal to e to the power minus G B beta by kT. Here K is Boltzmann constant. Now a problem has been given here as homework. Please solve this problem. Calculate the population n plus half of higher energy spin state of electron, that is ms equals to plus half or alpha spin, relative to the population n minus half of lower energy spin state of electron, that is ms equals to minus half or beta spin at 300 Kelvin temperature in an external magnetic field of a strength 3000 Gauss. This problem will be solved with the help of Boltzmann distribution law, and the answer of this problem is 0.9986. This is the population of higher energy spin state of electron relative to the lower energy spin state of electron at 300 Kelvin temperature if the applied magnetic field strength is 3000 Gauss. This is the answer. Solve the problem. Its solution will be given in the next video. There is another problem for homework. Calculate the value of nuclear magneton using the following relationship. Nuclear magneton beta n is equal to Eh by 4 pi mpc, where mp is mass of proton. We have already seen that there is a term beta which is called Bohr magneton, and Bohr magneton beta is equal to Eh by 4 pi mec, and the value of beta we have already calculated in the previous video. On similar pattern, the value of nuclear magneton, that is beta n, can be calculated by putting the mass of proton here. The answer of this solution will be 5.05 into 10 to the power minus 24 erg per Gauss. Please try to solve this problem. Its solution will also be given in the next video. There is time for another homework. Calculate the population of higher energy spin state of proton relative to its lower energy spin state in an external magnetic field strength of 15,000 Gauss at 300 Kelvin temperature. If the energy difference between two spin states of proton is G beta B, where the value of G is 5.585 and the value of beta we have already seen in the previous problem for homework. The answer of this problem will be 0.999898. Solve this problem. The solution of this problem will be given in the next video. We have calculated the relative population of higher energy spin state and lower energy spin state of electron in the previous homework problem. But in this problem, we have to calculate the population of higher energy spin state of proton relative to its lower energy spin state in an applied magnetic field strength of 15,000 Gauss at the same temperature, that is 300 Kelvin. Its answer is 0.9999898. Now, on the basis of answers of the previous homework problems, some conclusions can be drawn. The magnetic moment produced by a spinning electron, that is beta, and its value is 9.27 into 10 to the power minus 21 erg per Gauss, and this magnetic moment produced by a spinning electron is about 660 times greater than that produced by a spinning proton, and its value is 5.05 into 10 power minus 24 erg per Gauss. This is the magnetic moment produced by a spinning electron, and it is the magnetic moment produced by a spinning proton, and it is clear that it is obvious that the magnetic moment produced by a spinning electron is greater than that produced by a spinning proton. This difference arises due to a smaller mass of electron than the mass of proton. The expressions for magnetic moment produced by electron and proton are given here. This is the magnetic moment produced by electron, a spinning electron. This is the magnetic moment produced by a spinning proton. It is EH by 4 pi MEC, and it is EH by 4 pi MPC. The mass of electron is much smaller than the mass of proton, and this is why the value of beta is about 660 times greater than the value of beta n. That is, the magnetic moment produced by a spinning electron is greater than the magnetic moment produced by a spinning proton. Compare between proton magnetic resonance and electron spin resonance spectroscopy, NMR spectroscopy and ESR spectroscopy. We have to compare between these two branches of spectroscopy. In the first column, we have property. Here we have PMR spectroscopy, and here ESR spectroscopy. Magnetic field strength used in PMR spectroscopy is about 15,000 Gauss, while in ESR spectroscopy it is 3,000 Gauss. 15,000 Gauss is higher magnetic field applied in PMR spectroscopy in comparison to 3,000 Gauss magnetic field strength applied in ESR spectroscopy. Region in which a spectrum is obtained. PMR spectrum is obtained in the radio wave region of electromagnetic spectrum, while the ESR spectrum is obtained in the microwave region. Magnetic moment produced by a spinning proton or electron. The spinning proton produces a magnetic moment equal to 5.05 into 10 power minus 24 erg per Gauss, while the magnetic moment produced by a spinning electron is 9.27 into 10 power minus 21 erg per Gauss. This is higher value in comparison to this. The value of G for a spinning proton is 5.585, while that for a spinning electron it is 2.0023, both in the free states. Lower a spin state. In the case of a spinning proton, Mi is equal to plus half has lower energy than Mi is equal to minus half, while in the case of a spinning electron, Ms equals to minus half a spin state has lower energy than Ms equals to plus half. Population of higher energy spin state relative to the lower energy spin state in the case of proton is 0.9999898, while in the case of a spinning electron it is 0.9986. It means in the case of a spinning proton, the energy difference between two spin states is smaller and accordingly the difference in population of two states is also small. While in the case of a spinning electron, the population of higher energy spin state relative to lower energy spin state is relatively lower in comparison to proton. Sensitivity PMR spectroscopy is less sensitive due to this a smaller difference in the population of higher energy level and lower energy level, while the ESR spectrum is more sensitive due to greater difference in population of higher energy level and lower energy level spin states. There is a notable fact: the energy difference between two spin states of electron is greater than the energy difference between two spin states of proton due to greater magnetic moment produced by the spinning electron than a spinning proton. The energy difference between two spin states of electron is greater than the energy difference between two spin states of proton due to greater magnetic moment produced by a spinning electron in comparison to a spinning proton. We have already seen that the energy difference between two spin states of electron is G B beta. The value of beta is higher, and therefore this energy difference between two spin states of electron is greater than the energy difference between two spin states of proton, which is equal to G B beta n. The beta n has lower value than beta. The higher the energy difference between two energy levels, higher the difference between energy of two energy levels. If this value delta E is larger, the population of higher energy level, that is Ni, in comparison to relative to the population of lower energy level, that is N0, will be lower. If this energy difference is higher, the population of higher energy level relative to lower energy level will be smaller. Smaller the population of higher energy level relative to lower energy level, as the energy difference between two energy levels increases. And if the population of higher energy level is smaller, greater the probability of transition from lower energy level to higher energy level. If the population of this excited state is smaller, there will be greater probability of transition from lower energy level to higher energy level, and accordingly greater will be absorption probability. That is, greater absorption of EMR will take place during this transition, and the greater will be the sensitivity of the measurement. If greater number of photons are absorbed during the transition, the sensitivity of the spectrophotometric measurement will be higher. This is why ESR technique, electron spin resonance spectroscopy technique, is more sensitive than NMR technique. Thank you for watching the video with concentration. Please like, share and subscribe it.